The first group up is going to be engineering the next generation airplane, and here they are.
I'm David Froletsky.
I'm Pratyush Sharma. I'm Brandon Webster.
I'm Jacob Davenport.
And I'm Nicholas Ferraro.
And we'll be talking today about engineering the next generation airplane, which was our GSET project this year.
During this presentation, we're going to be talking about first the problem that we wanted to solve, and the background of our research, the design of our plane, computer analysis and construction involved in this, our testing, our results, and the conclusions we got.
So before we begin, let's quickly take a look at the aircraft industry today. It really hasn't changed much in the past 40 years. Planes, the concept of planes, are still the same. They look the same, they fly the same, they have very similar engines. However, in the past couple of years, there have been certain advances that have the potential to revolutionize the aircraft industry, particularly the invention of very light and efficient electric motors, as well as the invention of very light and high-capacity electric batteries. And electric motors have the potential to replace jet engines in the near future, and our project focused on their applications in the military. Particularly, we focused on heavy aircraft. The problem with heavy aircraft in the military is that they often have to take off very quickly and gain altitude very quickly to avoid fire from enemy troops on the ground. And it's very dangerous because they fly very close to their stall speed. And if they reach their stall speed, they literally fall out of the sky. It's also a lot of wear on their engines because the engines aren't designed to run at full throttle, which they do during takeoff. So our idea was, why don't we replace the turbine engine with an electric motor, and then have RATO technology assist during takeoff. And what RATO is, it stands for Rocket Assisted Takeoff Technology. And we'll get into more detail later on in the presentation of what that is and how that works.
Before we go into that, here's some basic concepts in aerodynamics. First, a plane has weight, which pulls it towards the ground, and to oppose that, it needs lift, which is generated mostly by its wings as it moves through the air, which pushes it upwards. And as it moves through the air resists its motion in a force called drag. And to oppose that, it needs thrust, which is generated by the plane's motors.
So we mentioned RATO. It stands for Rocket Assisted Takeoff Technology. It's very simple. Imagine you have rockets strapped to the side of your plane. They help accelerate down the runway and then take off quickly. Then they then turn on, they then turn off, and the regular engines take over. So it was first introduced during World War II when engines on airplanes weren't powerful enough to get planes off the ground quickly. It was really popular after World War II when jet engines were developed, but they also still weren't powerful enough. But nowadays, when we have very powerful jet engines, RATO isn't being used anymore because the engines can get the plane off the ground by themselves. But because RATO isn't being used anymore, it's the engines that are taking all the wear and stress from the takeoff. Next thing we mentioned was the electric motor. So why do we want to replace the jet engine with the electric motor? What are the advantages? Well, the electric motor is a lot lighter. It's also a lot more reliable because there's only really one moving part. Because of that, it's also a lot easier to maintain, and it's easier to control because it can spin up and slow down a lot quicker than the jet engine. It's also quieter, which is great for military applications. The only problem with the electric motor is that for takeoff, if you wanted to take off with the electric motor, you'd have to have an unrealistically large battery. So it's pretty evident that you can't use the electric motor for takeoff. So our idea was, why don't we supplement the electric motor with RATO? So what would happen was we'd have rockets help our plane take off, and then have electric motors switch on for sustained flight.
We began our construction by drafting our plane and finding the dimensions as seen in this picture. We knew our plane was going to be around 2.5 to 3 pounds, and this would be large enough to realistically model, yet small enough to fit within our time and budget constraints. We applied this weight to find a wing loading, or the surface area of the wing. We then applied an aspect ratio of 5, which provided a good compromise between lift and stability to get a wingspan of 48 inches and a chord length of 9 inches. Finally, we decided our fuselage would be a rounded triangle shape. This would allow the plane to be aerodynamic in flight, yet have a flat bottom which would safely secure cargo.
After we finished two-dimensional drafting, we moved on to 3D modeling. We originally used a program called Blender, which you can see here to visualize our ideas. Then we moved into a program called SolidWorks, which you can see on your right, which is a technical modeling software. We used it to get an idea of the center of gravity of the plane, which is crucial for aircraft flight. Without a proper center of gravity, a plane won't fly. It also allowed us to estimate the weight of the plane with all of its components installed. Lastly, it gave us the proper dimensions of the plane and allowed us to visualize it in a three-dimensional space. Next we moved on to a Depron Prototype. The prototype allowed us to get insight into any problems that the plane might have. Particularly, the prototype was tail heavy. Knowing this ahead of time allowed us to modify our design so that we could address these problems in our real plane.
Next, we began the airfoil design. An airfoil is basically the side view of the wing. So what we did was we first used the University of Illinois database to look up different airfoils and chose our top 11 candidates based on what we felt had the most aerodynamic shape. Then we ran it through three softwares known as Xfoil, VisualFoil, and ANSYS, and this helped us find our best candidate. First, we ran it through Xfoil. This showed us our lift to drag ratio, and it also showed us the distribution of pressure across the airfoil, as you can see in the chart over there. And it showed us that our strongest contender had a lift to drag ratio of 93.09, which is a very high lift to drag ratio. Then we ran these 11 airfoils through a software known as VisualFoil. This once again verified the lift to drag ratio given to us by Xfoil, and it also showed us the maximal angle of lift, which is the angle of takeoff where the lift acting on the plane is highest. This is important to us as we need a high maximal angle of lift in order to have a quick takeoff, and this helped us further eliminate our choices down to 3 airfoils. Finally, we used a software known as ANSYS, which used computational fluid dynamics, which basically simulates the airfoils in different scenarios with different variables. And in this, we conducted a second-order differential study with 300 iterations, which basically means that it would give us the most accurate results given our limited computing power. We found that the airfoil best for us was the NACA 9512, as it was it had the best pressure distribution and it generated the least turbulence. And as you can see in this chart here, there's a very little red on the airfoil showing that it took in the pressure pretty well, and pressure and turbulence are the most important variables on the airfoil, which is why they were tested.
So before we started building our aircraft, we made sure we had all the parts that we would need. First of all, we needed foam that would be sturdy and lightweight, and we used things such as carbon tubes and balsa wood to support it. And you can see here all the components and electronics we had to get so we would be able to control the plane. And so we made sure we had all these before we started construction.
Here you can see an example from a software we used called ECalc. ECalc allowed us to test for the specifications of various electronic equipment used inside of the plane. You can see we tested the battery, the motor, and the propeller, amongst other components.
When we began construction, we realized that we would need specialized tools to perform specific actions on the plane. For example, over on the right, you can see a wire cutter, which we needed to accurately and quickly cut out sections of the plane. We also used a leveling device with the hot wire cutter, which allowed us to be even more accurate in our cutting. Lastly, we needed sanding blocks. We needed to create sanding blocks to smoothly cut out or sand off portions of our plane to make it more aerodynamic.
We began construction of the body with the nose cone. To create this, we stacked 4 pieces of foam together and used a hot wire cutter along with a top and a side view to cut out the basic shape. We then used sandpaper to mold the shape into its final exterior, as seen on the left. We used a drill, as you can see on the right, to hollow out the nose to provide room for electrical equipment and save weight. The body was constructed in a very similar fashion. You can see in the top right that we used the hot wire cutter to completely hollow out the interior for electronic equipment. On the bottom right, you can see we put a plywood sheet which would allow our wing saddle to rest easily and prevent the wing from moving during flight. Finally, we constructed the tail. The tail was constructed very similar to the previous parts using 2 side templates.
After this, we constructed our wing. We basically took a foam board with very similar dimensions to our wing, and then we lined up 2 templates of our airfoil on opposite sides of the wing and nailed them in. And then we ran a hot wire around the templates in order to cut out the foam into the shape of our airfoil. And then what we did was we put a carbon rod through the fuselage in order to connect the wing to the fuselage, and then we placed a wing saddle on top in order to properly secure the wing.
Next, we created the control surfaces, which allowed the pilot to control the flight path. All the control surfaces were either made out of Depron foam or wood. You can see on the bottom left, we attached them using an alternating weaving tape method. This allowed the control surfaces to stay attached to the plane during even the most turbulent flight, yet allowed the servos to control their movement.
Next, we had to do the electronics and wiring of the components of our plane. The diagram on the left shows how the servos, the motors, the ESCs, which are the electronic speed controllers, all connect to the battery and the receiver. And then on the picture on the right, you can see how all the wiring looks when it's outside the plane, and that plywood sheet fits inside the fuselage, so all of that is stored inside. Then we had to create the motor mount to connect our motor to our plane. It's made out of two materials, plywood and balsa. Plywood is the harder of the two woods, so that was used for the front plate that attaches to the motor and the top plate which attaches to the wing. And then balsa wood was used for the support struts that connect those two pieces.
For our landing gear, we decided that the gear would need to be strong so that when the plane landed, the plane did not bottom out. But we also realized that the landing gear needed to be somewhat flexible so that it had some give to it, and upon landing it did not immediately snap. Also, our front wheel needed to be steerable, so we attached it to a servo.
As our plane was created in separate parts, we needed to assemble it. What we did was we glued the tail to the fuselage, and then we embedded magnets within both the head and the fuselage, and wooden dowels within the head and holes within the fuselage in order to properly secure the head to the fuselage. And then we put carbon rods into the fuselage to connect the wings to the fuselage, and finally we put wires from the wing motors into the fuselage in order to connect the motors to the battery.
Because we decided to use rockets for our plane, we needed to create a rocket mount that would hold the rocket stable during flight so it did not negatively affect the flight of the aircraft. So we created a model of the rocket mount in a program called Blender, which you can see here. We then printed the rocket mount using a RepRap 3D printer, which you can see on your right. We also needed to test our rocket mount to ensure that it could withstand the heat and thrust generated by the rocket. We also embedded the mount in foam to ensure that the foam that the plane is made out of would also be able to withstand the thrust generated. We then attached it to a known working plane to ensure that the rocket did not negatively affect the flight of the plane. We used Class C model rocket engines originally, but we decided we needed Class D engines, which are basically larger and provide more thrust than Class C engines, to ensure that we would have enough thrust upon takeoff. We also needed to test our motors, motor mounts, and how the motor mounts attach to the wing to ensure that all the connections would be strong enough to withstand the thrust generated by our motors. We also needed to test the servos and control surfaces to ensure that they were working before we began flying. Once we were satisfied with all of our individual parts testing, we coated the plane in tape to ensure that the outside would be smooth and aerodynamic.
So next was actually to see if our plane could fly. So we had 4 tests that we wanted to carry out. First test was just to get the plane off the ground, see if it could fly. We were going to take off, fly straight, and land. Second test was with full throttle. We were going to take off, circle around the airfield, and land again. And then the third and fourth tests actually tested our rockets. So for the third test, we're going to have 50% throttle on our electric engines, and using the D12-5 rocket, we're going to take off, recording the takeoff distance. And then we would do the same thing for the fourth test, just with 1/4 throttle instead of half throttle.
So here's a video of our second test where we used full throttle and without a rocket. As you can see, it takes off pretty smoothly and flies smoothly. So we wobbled it in the air a little bit to make sure the wings and the plane were sturdy and to make sure it responded well. So then we just circled around and came in for a landing.
I'm quite shocked it is.
We were shocked.
Yes. And we landed, and obviously no damage to the plane.
So then we actually had to test the rocket. So the rocket is ignited on the ground. This is the third test with half throttle. It takes off, then the rocket flies out of the plane with a charge. We'll see that about right now. That's to make the plane lighter, so that it flies easier. And you can see how smoothly it flies now that we're not wobbling it and not trying to test anything. So it flies around and comes in for a landing. We'll show you that. Next was the 1/4 throttle test. So that wasn't as successful. It wasn't enough thrust to get our plane off the ground, and you'll see that right here. That's the rocket.
Now on to the results of our flight testing. We found that with no rocket and at full throttle, the takeoff distance of the plane was 40 feet. And at half throttle with a D12-5 rocket, the takeoff distance was 17 feet, which means that the takeoff distance was more than halved. And we also found that there was no significant damage to the rocket holder or the plane, and that there was no damage to the aluminum foil shield around the rocket holder, showing that there's no real risk of fire.
In conclusion, we determined that the data found in all of our trials supported our original goals. We shortened our takeoff distance by 23 feet, which was a decrease of more than 50%. We showed that as a proof of concept, RATO technology coupled with electric motors could provide a viable solution for heavy cargo planes.
We would like to thank Director Eileen Rosen, Assistant Director Jean-Patrick Antoine, Residential Teaching Assistant Bob Ngala, our project mentors G. Panchal, Andrew Doroshenko, Jim Pagani, and John Santek, and our sponsors.
Questions?
Good job.
Thank you.
Beautiful.
Did you really do that all in just 4 weeks?
3.5.
We decided sleep was not necessary.
Yes?
Where's the plane go now?
That's a very good question. That is still up in the air, pun not intended. Yes?
Who was your pilot?
One of our mentors was, well, actually 2 of our mentors acted as pilots.
Yes?
First, congratulations. You talked a lot about the design and assembly of the plane. How did you control the plane with the remote control?
Well, it's got, I can show you inside, it'll be very quick. Basically, inside you've got your battery, then you've got a receiver. You use this controller to control the plane. This controls the thrust. This is the yaw, turning it like this. This controls the ailerons, banking it like that. And then this is the elevator, making it go up and down. So, yeah.
In your pictures, I saw that you were using 3-bladed props, and now here in the model, you're using 2. I'm just wondering what went into that decision.
The 3-bladed props were slightly different. They were actually shorter than the 2 props, and we had done ground testing, as you had seen before, where we attached the motors and powered them on a wooden table. And it was decided that the 2 winged props that were longer provided greater stability and prevented the plane from shaking as much in flight.
Is that all the questions?
I'm just curious, the nose part comes up very quickly. So how did you fasten that?
It's, as you can see, we use balsa to kind of secure it in place, but there's also magnets on here which hold it in place during flight.
Actually, in our first test, which we didn't show, where we just took off and landed, we had a little bit of an issue with the wind, and our plane actually landed nose first. And the nose came off, which was a good thing, because that's how our plane was designed. And because it came off so easily, we experienced no external or internal damage.
And also, you just mentioned that you did use for cargo application, cargo destination.
Okay, if that's all the questions, then we're going to move on to the next presentation.